We are continuing our lecture series, and today we are looking at Introduction to Linear Programming. So, by way of definition, we can say a linear programming is a mathematical technique for solving linear optimization problems subject to linear constraints. So, in a linear programming problem, one studies the best way to allocate limited resources in order to achieve a maximum objective. Okay, that is if you are looking at it in terms of making profit, we talk of maximization. If you are looking at it in terms of reducing cost, then we look at the minimum cost available. So this particular topic can be applied in various ways. And another example where we can use linear programming is where you have allocation problems, we have transportation problems, distribution problems. So you can use a linear program to actually do all these things using mathematical formulas. So let's say for example, that you are a manufacturer. Of course, you'll be producing several different types of goods. The only problem you will be looking at now is, for example, the labor hours that you have available to you. And the second one could be the machines that you are using. So the labor hours, people are not able to continuously work. Even machines, they break down at some point. So if for the 24 hours you have a limited number of hours that you can use in performing this task, and the machines too, they get tired at some point. So you will need to look at these as constraints in order to formulate a mathematical problem to solve it and be able to get the optimal solution. So the question now is, how should you allocate the labor and machine time so as to produce enough items to meet the demands in the market? And of course, as you are doing this, you are thinking of also minimizing the cost that you incur in producing all these things. So first, let's look at the properties of a linear program. One, the relationship between variables and constraints must be linear. So we're looking at linear, so all the variables must be linear. Linearity, we are looking at the coefficients being linear. So that is the linearity we're talking about here. The model must have an objective function too. So maybe your objective is to maximize profit, or your objective is to minimize the cost. So whichever way it is, you must have an objective function. Third, the model must have structural constraints. So the constraint that you have, you would have to define them mathematically. They should have a relationship, a mathematical relationship. The last but not the least property is that the model must have not negative constraints. If you are going to produce, let's say you're going to cook food, if you don't have the materials for the food, you will not start the cooking. So you can never have negative materials. We don't have negative constraints in this case. This is how a standard LP problem looks like. First, just like the properties we have identified earlier on, you have a maximization function, then subject to some restriction. The restrictions here are what we call the constraints. So the function being maximized here is our C1 x1. So let's see here, that is the function that we are maximizing. So this C1 x1 plus C2 x2 up to Cn xn is what we call the objective function. Now the restrictions normally are referred to as, you've heard me mention constraints already. So the restrictions are what we usually call constraints in a linear programming module. So the first m constraints, that is those with a function of all the variables ai1 x1 up to ain xn on the left hand side, are sometimes called functional constraints. So that's this functional constraints, all these are functional constraints. And then we can have a similar one for the non-negative constraint. And that will say if we can have a similar constraint for the xi's. So you have the xi greater than 0. So every, let's say, x1 should be greater or equal to 0, x2 should be greater or equal to 0, and then xn should be greater or equal to 0. So none of them is going to give us a negative value. That said, let's look at some terminology. You may be used to having the term solution to mean that to mean the final answer to a problem. But the convention in linear programming is quite different. Here, any specification of the values for the decision variables, what are our decision variables? The x1, x2, up to the x that we stated earlier, is called a solution, regardless of whether it is a desirable or not desirable. Okay, so different types of solutions are then identified by using an appropriate objective function. A feasible solution is a solution for which all the constraints are satisfied. That is a feasible solution. We'll use a graph to demonstrate that. So let me just draw that one here. If we have this one as x here and then y here, and we have a line, let's say this is the line. Now the equation of the line probably is, it is not a correct equation. I'm just giving it something. X plus y less or equals to some value, let's say 5. This is the equation that will give us this nice line that we are seeing here. Then we can say that any value that is below the line satisfies the graph because it's talking of less than or equals to. So if I pick any point between these inside this triangle and put inside here x1, y1, I'm going to get the value to be either less than or equal to 5. So it means that everyone here is satisfied. Now, this is what we call a feasible solution. All the solution, the points here that satisfies our equation or inequality, we call that the feasible solution. Infeasible solution, on the other hand, is a solution for which at least one constraint is violated. So if this is the case, and unfortunately we happen to have just a single point in the middle that did not satisfy this inequality, then we say that the whole area is not feasible, called infeasible solution. The feasible region comprised of the collections of all feasible solutions. So all the feasible solutions where they are found, we call that the feasible region. So the triangle is called a feasible region. It is possible to have a problem that will not have a feasible solution. Let's look at optimal. What is optimal solution? A feasible solution that has the most favorable value of the objective function is what we call the feasible solution. The most favorable value is the largest value if the objective function is to be maximized, whereas it is the smallest if the objective function is to be minimized. So in this case, this could be the points that will lead us to whether minimum or maximum. So most problems will have just one optimal solution. Our attempt to find the optimal solution, most times we look at the corner points, especially when you are considering the graphical method in solving your equations. So in this case, the points that are already marked the corner constitute the corner points. If we had another graph going through this way, then their intersection will constitute another feasible region, and this would have been out of it wouldn't have been a feasible region, so we would take that off and consider this as part of the corner point feasible solution. Let's take an example so we can see how this is done. Now, the best way that you can actually do this without a struggle is to draw a table and put them inside. Okay, so let's see how we can formulate a mathematical problem from a question. 4 different types of metals, namely iron, copper, zinc, and manganese, are required to produce commodities A, B, and C. To produce 1 unit of A, 40 kg of iron, 30 kg of copper, 7 kg of zinc, and 4 kg of manganese are needed. So let's take all this and then rule here because we will need to come back here for something for these numbers. So similarly, to produce B, we need 70 kilogram of iron, 14 kilogram of copper, and then 9 kilogram of manganese. So that means that zinc is missing, it's not needed here. Then product C, we need 50 kilogram of iron, 18 copper, and then 8 kilogram of zinc. Manganese is not needed in this one. So the total available quantities of metals are 1,000. This is the limited resources that we spoke earlier on. That is how we are limited to 1,000 kilogram of iron. If you need more than that, you won't get. You can either use the 1,000 or you use less than 1,000, but you cannot use more than 1,000. What you don't have. So 500 kilogram of copper, 200 of zinc and manganese respectively. The profits for producing each of the produce A, B, C are 300, 200, and 100 Ghana cedis respectively. So our problem is to formulate the mathematical model. Now, the ability for you to answer the question or to solve it relies on you being able to identify and write out the model properly and accurately. So if you make a mistake here, your solution is going to be wrong, not because you didn't calculate it well, but because you got the model wrong. So you can have a wrong model and you have a correct solution based on the wrong model, but that won't solve the problem. Our objective is to solve the problem, not to solve something else that is correct. Okay, so the best way that we can have this done is to actually put this in a table. That will make it a less difficult for us to write out our equation. So let me create my table here. Okay, I have three products. So I want to put the products here. You can see. Then I have the materials. I have the iron. I have the copper. I have the zinc, and I have the manganese. Okay. Now I will extend this a little because I want to write it available materials down there after I have finished. So let's look at A first. A, we need 40 kilograms iron, we need 30 kilograms of the copper, we need 7 kilograms of the zinc, and 4 kilograms of the manganese. What profit are we going to get to do this combination? What profit are we going to get? We are going to get 300 Ghana cedis. Next one, B. B needs 70 kilograms of the iron, 14 kilograms of the copper, and then 9 kilograms of manganese. So we put 9 here. Zinc is not mentioned, so it means zinc is not required in making product B. So I put 0 here. And what profit am I going to get when I finish with this product? I am going to get 200 Ghana cedis. Product C would require the mixing of 550 kilograms of the iron, 18 kilograms of the copper, and 8 kilograms of the zinc. So here, no manganese, I put 0 there, and I get a profit of 100 Ghana cedis. Now, what are the constraints? What is the available iron that we have? We have just 1,000 kilograms of 1,000 here. Okay. Then I have um, copper. Copper is 500 kilograms. Put 500 here. Zinc is 200, and then manganese is 200. So this is the table that describes the whole question that we just read. The next thing is to now write out your equations one after the other. So the first one is to maximize your objective function. Maximize. Let's say we are maximizing profit. Okay, so Z is equals to, you can decide to put any letter but define what the letter stands for. So my Z here is representing the profit. Okay, we want to make profit. So I have maximize Z equals to 300 of A plus 200 of B plus 100 of C. Subject some constraints. What are the constraints? One is the iron constraint. Iron. So iron, what is how much is iron given to A, iron given to B, and iron given to C. So I have 40A plus 70B plus 50C. This combination should be less or equal to 1000 because we do not have more than that. Next one is copper. Is our copper constraint. We have 30 to A, 10 given to B, plus 18 given to C, and this should be less or equals to 500 kilogram. Zinc constraint, we have 7 of given to A, plus we don't have a B, so that is 0, plus we have 8 given to C, so 80 less or equals to 200. Similarly, manganese constraint is equals to 4 given to A plus 9 given to B plus nothing given to C, so that place is 0, less than or equals to 200. So these are our constraints. Of course, the last but not the least constraint is your non-negativity constraint. So let's look at algorithms. What are the methods designed for us to use in solving linear programming problems? One is the graphical method. So the graphical method, all you need to do is simply draw a graph using the equation, the constraint equations or inequalities. Then you look for the feasible region, look for the feasible solution, and the optimal one. The one that is going to give you either the maximum profit, the largest value, or the minimum cost, the smallest value, depending on the problem you want to solve. You want the simplex method, that is also an algorithm that we have to go through processes until you get to the final stage where you pick out your a combination of your solution. Now you have the northwest corner method, we have the least cost method, and we have the maximum cost method. These are the algorithms that we are going to look at in the course of this series. Okay, so let's look at the first one. What? How do we perform a graphical method?